Okay, thank you everyone. Welcome in my session on hands-on programming languages. I'm Bart. I'm working in Redmond at the cloud programmability team at Microsoft, where I tend to look at quite some language innovation related things from time to time, especially to express those transformations on big data. And so one of the things I'm kind of keen on is everything that has to do with functional. However, in this talk, they've asked me to sort of step back a little and take a look at, more trends in programming languages. And yesterday, when I was actually in my hotel room, I was thinking, like, in how many languages could I write Hello World? Because that's kind of a good indication of, how many languages you're familiar with to sort of express yourself. And I still believe that languages are the most important piece of expressiveness that people actually have. So I think it's worth to step back every once in a while and take a look at what we have on the menu. So actually, to get started, I wanted to rewind the clock about 18 years when I started programming. I was actually a teenager in elementary school, and people actually asked there to do those horrendous sums, just computing some big numbers. And it turned out that I was one of the few people who was done the earliest with my sums. And the teacher actually said, well, you can just validate your sums using this little ugly computer in the back of the room. So let's actually step back and take a look at how programming looked about 18 years ago. And so I have DOS over here. Since I'm running 64-bit Windows, I need to use some emulator because we don't have the virtual DOS machine anymore. But so I can mount some drive here, which is now C. And actually, I can still run GW Basic today, which is basically the language in which I started programming. And basically, what they asked us to do, just to validate our sums, was to write something like question mark 3 plus 4, and it just prints 7, and yes, okay, my sum was right. However, I quickly realized that you can also write programs in this thing, that you can do things like, line number 10, print hello, line number 20, go to line 30, which is totally useless, and then print world. And you can press F2 and the thing runs. And so I started copying a lot of that code from books and trying to be smarter than the people who wrote the book by, for example, renumbering everything to be 1, 2, 3, and 4. And then I came to the conclusion, well, if I need to insert some piece of code, I'm totally screwed here. So I realized that we need more abstraction, and I sort of wanted to get out of the world of BASIC, or actually GW Basic, and started learning about new paradigms. And that's something that you often need to do, step out of your comfort zone and start looking at other ways to express your thoughts. So I actually had the hardest time preparing this demo because I didn't find how to quit GW Basic. Apparently the command is system, so that took me quite a while to figure out. Now later I actually stepped up to Quick Basic and just take a look at this thing. It starts to look a lot like Visual Studio already, like almost 20 years ago. I have an immediate window, I have some screen at the top. I don't need to do line numbers anymore. I have something better than go-tos. And so that was kind of a refreshing thought that I can now write things like this. And notice how the engine here sort of has IntelliSense or recognition of the language elements by putting things into uppercase, which is kind of interesting. It's the same as syntax highlighting today. You can set breakpoints, you can press F5, you can go to the immediate window, we have a mouse cursor, and take a look at the state of the program. We can even have a watch window here that just kind of watches what the value of I is. Like, not that much has changed over the years when you actually look at the things you can do here. And I can just go through it, and you see at the top, the watch window is actually revealing the next value of the number. So we have some IDE experience here, but from a language point of view, things have changed quite a bit. We don't have to do this manual looping anymore using go-tos. So procedural programming came around, and we had those imperative control flow constructs added to languages. Later, I stepped up to do VB-DOS, and yes, I can run this thing over here as well. I have some nice designer with windows I can sort of shuffle around. That's, kind of a refreshing thing again. And now we'll see that we can do things more declarative. Like, declaring a UI is not something you have to write code for anymore. You can actually just do new form. And instead of doing ASCII art, you can put a command button up here. You can resize the thing. You can basically change the color, select the property that you want to change. Like, not much has changed compared to today's Visual Studio, right? And, we can say hello, and we can even, attach an event handler. We can just do some magic here, but then we select command 1 click, add it in active. We can say print hello. Whoops. We can press F5, and yes, I have a window, and it's even, you can resize it, you can drag and drop it, maximize it, minimize it. So there's a lot of framework code being added to the platform now that allows me to do this kind of things pretty quickly. We have rapid application development now in Visual Basic 1.0. And so that was sort of where I started hacking with computers. But if you look at the experience, well, yes, tools have become more extensive. We got much more frameworks, but the basic ideas of, this debugger interaction, designer interaction is still pretty much the same. So let's take a look at the past briefly and then sort of go into some of the thoughts of things that we are seeing right now. So everyone has seen this picture plenty of times, I guess, how we got from assembler all the way to managed runtimes, garbage collection type systems, all those things, by going through procedural and object-oriented programming somewhere along the way. Now, of course, there is some interesting thing in here. Lots of people prefer to be in the top right quadrant of this slide. The more services the runtime can give me, well, the better. I don't have to do that much. But it's still true that, the low-level languages like assembler give you all the control that you need to sort of control the machine, to program the machine. And as we actually start looking at those hardware trends that are shaping up, it's actually interesting that not just this axis of numbers is holding true. The fact that clock speed got quicker or faster, that memory got much more extensive and you can store much more, and that disks got a lot bigger. It's also the case that there are fundamental shifts in all those individual layers of the memory hierarchy, you could say. For example, at the CPU level, it's not just the case anymore that the basic assumption holds of having a single CPU. Now you have multiple cores, and that means that the programming model, well, likely has to change. It's not the case that your procedural code will just run in parallel on multiple cores. Same with memory. Some of the fundamental assumptions that the speed of going to memory is independent of where you're executing things doesn't hold anymore, because now we have this thing called non-uniform memory access. So that's something that definitely some low-level people need to add to the capabilities of the operating system before you can take advantage of it. So it's not the case that with higher levels of abstraction you can start to forget about the old days of assembler, because, well, still some people need to implement stuff there. And now the question is how much of that sort of leaks to the programming model of what people are doing. Same with hard disks. The basic assumption that a hard disk is way too slow to just have a chatty dialogue with might still hold true, but the relative numbers are changing quite a bit if you look at SSD. SSD memory or SSD hard disks have very good random reads and random writes. So it's no longer the case that maybe for certain applications it's just way too slow to go to the hard disk anyway. So some assumptions are definitely changing. So an important question now is, well, where do you want to aim in terms of language design, in terms of framework design? Do you want to go for those high levels of abstraction, which we'll talk about quite a bit, such as having richer frameworks, having new language features, have the runtime do much more for you than it did before? Or do you want to go for low-level plumbing, where we see a lot of evolution as well? Like we see new CPU architectures coming along quite quickly with regards to power consumption, small devices, all those things. Well, at MIX a couple of weeks ago, we showed Internet Explorer 10 running on an ARM processor. Well, somebody needs to write the freaking assembler in the compiler in order to make that happen. So we can't just forget about those kind of things. It's also the case for power consumption that might very well leak into your programming model. Like, how do you write applications that are good for the battery life or that basically don't consume much memory in the cloud, because our data centers need to be powered as well. So power consumption is also some of the new things that are coming across the board. And the rich capabilities of GPU is something we also want to enable. So we have those two opposite forces, I would say, between aiming higher to be more productive, but at the same time we cannot afford to sort of lose the connection between the two worlds. We cannot lose some of the rich capabilities of the hardware in adding new levels of abstraction. Let's actually tell two stories here that relate to this. So I have two axes here, a time axis of evolution, and then, I have some horizontal separation between two layers which I would call user space and system space, not to use user mode and kernel mode because I'm talking about something else here. I'm basically talking about the system space as being runtime services that you need in order to write your applications, and then the user space is the things that you're actually working on. So let's take a look at GPU acceleration as one case study. Well, for the longest time we've had DirectX APIs. And lots of people were extremely happy with DirectX APIs because they were just writing games. And later we said, well, some general purpose applications also would like to have graphics acceleration. So we create this thing called WPF and Silverlight, and so people can start writing applications there as well. But it's not the case that all different programming models had access to the GPU. Especially, it took all the way till HTML5 came around and the canvas element came around, that browsers realized, wait a second, we have those massive GPUs sitting there, but we are sort of disconnected with the programming story from the bare metal of the machine. How do we bring those things together? So people had to insert a layer, because otherwise you couldn't do anything in the web pages in order to make those new language features, if you will, like canvas is a new way of describing graphics in HTML, making that actually possible in your applications. Now, similarly, asynchronous I/O is even more of a terrible story in some sense. Like, if you look at hardware from 20 years ago, well, the idea of your CPU not having to be blocked while you're basically waiting for network traffic to come back or from the disk to sort of give you the data back that you requested, we have had APIs that can deal with that asynchronous hardware from the very beginning. So we had Win32 APIs, we had the Common Language Runtime exposing this stuff. Later we had some abstractions for the task parallel library. But the thing is, it took almost 20 years before we implemented something at the language level, being C# and VB next version, having async feature support to basically do asynchronous computations right inside the language. So you see that the disconnect between hardware capabilities, low-level capabilities of your platform, and things on top sometimes takes a long time to sort of shape up. And so, in essence, I would say that at the low levels, we cannot forget about those things. Also that, today when you have a phone, this thing has much more sensor than any other thing I've seen before. This thing has a GPS, has an accelerometer, has a gyro, has a compass, has all of that stuff built in. Well, at some point we need to talk to those things, and we're kind of lucky that the high levels of abstraction allow to forward that through. And it's not the case that our programming model needs to change significantly for those, but for some things it might, like the many-core thing. I think that will definitely surface in languages much more prominently. So now let's take a look at software trends. And I'm using a similar coloring scheme as 2 slides ago, where I sort of indicate by the color how close we are to the hot metal of your machine. When we talk about concurrency, well, clearly we need to have a good understanding of how multiple cores actually work in a machine before we can write meaningful applications. Just slamming some locks on something will not make your machine go faster. You will basically sequentialize all the operations. You need to know what's safe to do on multiple cores at the same time. So you need to have a very good understanding about the underlying hardware. Then on the total opposite end of the spectrum, we have declarative programs, where people say, I just want to tell the damn runtime what to do. Like, just, this is the thing I want to get as the result. And you go and figure it out through many layers of abstraction how that thing should actually be executed. So that's declarative programming. Think about issuing a query in a database. You don't tell, just open, table 1 and start doing a row scan over there and then do a hash partition over there and all of that stuff. No, you just say the thing you want to be done. And that might take, a lot of execution engine infrastructure to make that happen. Then we have dynamic languages, which are sort of in the middle, in a sense that, well, you want to up-level your level of expressiveness a little bit, because, well, if the type system is in the way, you're just too annoyed. So you say, like, dear type system, be more forgiving when I do something here. So you make things dynamically typed, but that doesn't work without having some runtime that understands dynamic typing damn well and can actually optimize those kind of things effectively. And finally, there is something that I've painted with, clear blue skies, which is functional programming that sort of promises heaven on earth. And I'm actually sort of in that camp. That's a new level of expressiveness where lots of people sort of are crazy about, but I wonder whether people sort of really get the essence of functional programming. And so that's the place where I actually want to start, because that's something, that's dearest to my heart. So the question is, will it blend? This is actually a pun on some American show, some guy who sells blenders has, those crazy videos on YouTube where he blends like iPhones and those kind of things. And so he always asks, will it blend? So will all those things sort of go together? Let's actually start looking at functional programming to begin with. So the core idea of functional programming is to take a radical different approach to how do you program a machine. So classically, we've had many people in the camp of there is some hardware, it's pretty real, it has a specification of a few thousand pages on the instruction set. Well, we better start just building languages that can target that instruction set. And so there we are in a camp of languages like C and C++ and Smalltalk. All those things sort of come from the same roots there, which is the reality of some particular piece of hardware you want to run on. On the other hand, you have the more mathematician kind of inspired people who say, well, if I just go to the library and I pick up a book from the 30s by Alonzo Church, it contains all the fundamental truths about how to compute something. It just has a mathematical formalism on how you compute, and that's what a computer does, I guess. So, it makes sense to sort of look at that. And so people from, the Lisp family, including things like ML and, Scala and Haskell, those people actually start from the top down. And so what has happened over the years is that definitely those people at the bottom say, well, we need to add levels of abstraction. And you can already see that, to my little evolution that I've done in the demo. You started with, GW Basic with goto statements, and later you got like, control flow mechanisms like for loops and if statements. Later you got, higher units of isolation and whatever. If you look at the functional guys, well, they have to be pretty real. There are certain things in that functional programming world where you might have space leaks because things are evaluated lazily and you assume that you have infinite resources available. Well, in that world, you need to do quite a bit of tricks to make things run effectively on real hardware. It's not the case that you can just give an Intel processor, the book of Alonzo Church from the 30s and say, just grok it and execute it. You need to be a little bit realistic there. So they've come down a little bit to sort of meet in the middle there. And today we see languages that are a bit of both, like Scala and F#. Those languages are sort of in that cloud where things are coming together. Now the question is, are they still fundamentally functional programming languages? So if you look around us, we actually see that this notion of a lambda expression just exists in every language that we look at today. If you would walk on the streets like 10 years ago and ask somebody about a lambda expression, most people will just look at you like you're crazy. But maybe there were a couple of Lisp people in there that have seen that lambda word and, have used it. But today, every programmer sort of has heard about lambda expressions. Even the C++ guys now have it. So things have really gotten real because like this functional concept has gone all the way down to those low-level system languages. Now the question is, how much is this really still about functional programming? So let's take a look at some very fundamental thing here. This is stuff that people write. And this is stuff that I was kind of surprised about when I did my first GW Basic programs, because this is just a poor choice of syntax. Like the equality sign has always meant that the thing on the left and the thing on the right is the same. Well, that's not really the case in this particular sample. Every mathematician will say that 0 definitely is not the same as 1. So something is kind of fundamentally broken about the way we think about programs, especially when we relate them together to, all those mathematical principles. So what's going on here is really that X represents a piece of memory, and every time we refer to X, we're basically referring it with implicit time. Like at some point, X might have that value. It's like a function that takes in time, and you say like, before the assignment, what's the value of X? And after the assignment, what's the value of X? Like there's something implicit going on if you look at this from a mathematical point of view. So let's actually define functions and sort of try to get to the essence here. Now if you look at a function, which people have seen in high school and likely got nightmares of, but A function basically just assigns a unique value to a set of inputs. If you ask the sine function, what's the sine of 30 degrees today, and you do that tomorrow, and in 20 years from now, and then just, at the end of the universe, it will still be 1/2. Like that function just uniquely assigns for every given input a particular output. There's no magic going on. There is no notion of time that's sort of implicit in this world. So why does that even matter? Let's actually take a look at some little piece of code that we will try to optimize. So here I have a piece of F# code where I basically do the following. I bind a certain name to a value. The first equal sign that you see in the slide here is basically giving the value of the right-hand side a symbolic name called equal. It's assignment, but it's something that's immutable from this point of view, because as soon as you do that, in the next statement of your language, you can't really assign to equal again. You can't mutate equal. It's once and for all, it's the value true or false, depending on what the evaluation actually yielded. On the right-hand side, the equal sign is in this case used for equality. And so I'm just comparing sine 0 with sine 0. And obviously this thing will return true. Now, if you look at this piece of code, you might ask, well, can't I just refactor out sine 0? Because that's the same thing all over again. I just have exactly the same piece of code in this expression multiple times. And in fact, in languages like F#, you can do that. You can say, basically refactor this piece of code into let sin 0 equals be sine of 0 in sin 0 equals sin 0. So you basically have introduced a little scope in which you evaluate the sine of 0, give it a symbolic name, and then refer to it multiple times. And arguably, this might be more efficient. For sine 0, well, the CPU has a built-in instruction for that. It won't make much of a difference. But, this is a fundamentally correct, way of refactoring this code. However, does this idea of common subexpression elimination actually carry on to all other places in the framework? So let's take a look at this piece of code. Let equal equals datetime.now equals datetime.now. Now you might be smart and say, well, datetime.now is computed twice. Let's just factor it out in some symbolic name called now, and then just compare those two values together. You've just changed the meaning of your program fundamentally, because datetime.now is maybe like a function. If you look in Visual Basic, it might even be called a function, function get now, and then it returns as datetime. But it's not a pure function because, well, clearly in this case it depends on time, but it basically, has different values every time you ask for it. So this is not the same thing. The bottom line will always return true. The top line might return true, might return false, I don't know. Will depend on the frequency of your clock, will depend where datetime.now is executing. If you have a multi-core machine, it might be that one datetime.now runs here and the other one runs there, if there are some smarts going on in the compiler. So I can't tell what the answer is for the first one. I can tell what the answer is for the second one. Something is really broken. So the thing that's going on is that we've mixed two functions here. The sine function is pure. The datetime.now function or the getNow function is not pure, which means that automatic optimization of my code, which we could actually do in the top case, cannot be done in general. So you've basically tied the compiler with its hands to its back in terms of, optimizing this code by eliminating common subexpressions. So why is it that we've sort of gotten accustomed to writing programs this way and just be very careful with side effects? Well, actually, if you look at this piece of C# code and this piece of F# code, it's actually quite obvious that this thing has to have some side effects. Because if you try to sell this to a pure mathematics guy and you say, like, here's the program, it costs like 49.95 euros, please buy it because it's a great program. And the mathematician asks, well, let me see what the input-output contract is of the program. He will say, well, the program returns unit, which means it doesn't return anything meaningful. Why do you try to sell me 49.95 for something that doesn't produce a result? So clearly, this thing is just totally based on the assumption that side effects are going on in the system. And that's the way, actually the first line of every C program is like a damn lie. It says static void main taking in something. Well, the void is not really true. Some side effects are going on. In this case, the side effect that makes it useful to run this piece of code is actually writing something to the console. So what's really going on here is that the type system that 99% of languages have does not track side effects, which means if you don't know about the side effects, you cannot start optimizing things just automatically. Like if we would know that sine 0, or the sine function, is a pure function and doesn't have side effects, and if we would know that datetime.now is an impure function and does have side effects, meaning it's reading from the clock, which is always changing, then we could optimize the first program, which used sine 0 with some common sub-expression elimination. But the second one, we would know that because it has side effects, we cannot start optimizing that piece of code. So in Haskell, actually, you can tell in the type system that actually side effects are going on. And that might be a very valuable thing going forward, actually, having those kind of annotations on types, because then you give much more power to compilers and runtimes to actually reason about the intent of your code. And you can have some pure piece of code in the middle that can be optimized quite efficiently because there are no side effects going on. Like if you're computing sine 0 plus sine 1, you could perfectly parallelize that on multiple CPUs, provided that you have lightweight parallelism. But if there are side effects going on, well, you cannot split that expression into two halves because, well, you don't know what's going on. And this guy is Philip Wadler. He's one of the guys in the Haskell committee. He actually lives in Scotland and is a professor at university over there. And so he brought this concept of monads, which is just an ugly word for some improved type system, to the world of Haskell. And that's actually a very promising thing in my opinion, but it requires you to be very disciplined about the way you write your code. In fact, you can't even do printf debugging in Haskell without changing the types of your program unless you do some unsafe operations. So when we look at functional programming, I think a lot of people actually confuse functional programming with programming in a functional style. Because if you look at Haskell, well, that's a pure functional programming language and it has a lot of features. And then people see that some of those features appear in a different language, like lambda expressions, and then they say, oh, at this point my language is functional. I fundamentally disagree with that statement because they do not define what a function is. If you look at a function in Visual Basic, it's not a mathematical function. It's a function that can have arbitrary side effects. So there is something sort of disconnected in there. However, I still agree with the fact that there are lots of desirable properties in those functional languages that might make sense in different ones. For example, pattern matching and algebraic data types is something that sort of improves the conciseness of your code quite dramatically, and I will show that in just a second, even though that's not something that, in my opinion, is the essence of functional programming. The essence of functional programming is to program with mathematically sound functions. And that gives you, control over side effects and those kind of things. Now, it's definitely the case that people start liking those functions more and more. If you look, for example, at things like JavaScript, they have a simple filter and map function on lists or arrays. Well, that's actually based on passing in little functions, which makes your code very concise. It's actually the same thing as LINQ, language integrated query. Immutable data structures are also something that's very promising for the multi-core evolution, because in that case, if you have immutable data structures, you can do things in parallel much safer because you know that things are not going to mutate. So where does F# fit in this picture? Well, F# is one of those languages that tries to combine the richness of a BCL, a base class library, which is a huge thing because, well, we have a tremendous investment sitting there, with functional style of doing things, which means typically your programs get much more concise. They are much more readable to certain people. If you're in the academic space or the banking space, financial space, those people like functional programming style much more than an imperative program style. And so that's actually where the value proposition of F# comes in, is basically taking some of those sweet features from functional programming and bringing them into a mainstream framework, such as the .NET framework. So let's actually take a look at a little piece of programming with functions. It's not functional programming because that's, in my opinion, the purest functional programming with pure mathematical functions. So let's take a look at some F# code here. So the thing I have here is basically a declaration of a data type that's called exp for expression. And it basically has two cases. It's called a discriminated union type. This is a type that contains either a const or an addition of two other expressions. So it's a recursive type, which you could also write in C# by basically having a little class hierarchy of a class called exp, then a subclass called const with a single property that has a value of type int. And then you could have a subtype of exp called add, which has a tuple, or basically two properties of type exp. And of course, you also want to implement equals and get hash code and toString and all of that stuff. So if you do that in C# or VB, well, you end up with like 2 pages of code. In F# that's just 3 lines of code. So that's actually a fundamental data type. Let's actually execute that. So the thing you're seeing at the bottom of the screen here is F# interactive. It's basically a read evaluation print loop where you can just issue those commands and just have them evaluated. In this case, I just pressed Alt-Enter, and then it sends that to F# interactive, so I can basically start prototyping things really quickly. Now I can create an expression tree here using my new defined type in a very concise manner. I can basically say I want to have an addition of 1 and 2, and then add 3 to that. So I have really 1 and 2 with parentheses, then plus 3. So that's an expression tree that represents this little piece of code as data. And so we could actually start writing some custom language here that in this case is just fundamental arithmetic. So let me actually just enter that in the console as well. You see that the indentation and the spacing has changed a little bit because this, what you're seeing on the screen, is really some kind of toString method that's implemented for us on the exp type. And now we can start writing some little functions on top of that. So let's actually write a recursive function that evaluates the value of this expression. So I can write a recursive eval function that takes an e, and now I can match e with either a const of value x or an addition of value a comma b, and then I will recursively evaluate a and evaluate b. So that's actually the only thing I need to do to write a little recursive function without having to do type checks and casts and all of that stuff. This is called pattern matching. So basically we're matching an expression of type exp, which is passed in as e, with either a constant, and if it's a constant, at the same time we're extracting the value x and we're returning the value x as the result of calling the function. That's what the arrow actually does. In case we see an addition, which contains by itself 2 expressions, which I now have symbolic names a and b for, and actually if I hover over this, you see that the compiler has already inferred that the type of this thing needs to be exp. It's implicitly typed, but it's still strongly typed and statically typed. Then I can do on the right-hand side, I can basically call the evaluation function recursively on a and b. And so this is a very concise way of declaring a piece of data, declaring a little function that pattern matches over the data structure and evaluates the expression. So I can now execute this piece of code. And now I can go, and as you can see, it has inferred the type of the function to be expression goes to int. The way it did that is by, looking first of all at the fact that you have discriminated on const and add, which are both subtypes, if you will, of the expression type. And then it has figured out that basically here you're taking const of x, and x has to be of type int. We're returning int, so the whole thing needs to return int as well. So we've actually inferred the type. And now I can do eval x. So you see that the result of that thing, of course, is 6. So what you've seen here is really programming with functions. I've just defined a little function here. It's also the case that the expression that I've defined here is immutable. So it's sort of getting a little bit towards the purity thing, but the fact that I can talk into any arbitrary piece of BCL code, which might have some side effects, of course is desirable, because without side effects most programs are useless, but that doesn't make it into a fundamentalist pure functional language. Yet it's still very concise, and in a lot of domains it might actually make sense to write code using a language that's this concise. So let's go back to the slides and sort of wrap up the section on functional languages. I have some photos in here of some good-looking people. Those are people from the Haskell community. Eric is actually my boss, and Simon Peyton-Jones is one of the designers of the Haskell language. He works in Microsoft Research in Cambridge. And they actually draw this picture quite often when they talk about Haskell. They say, well, there are 2 axes to the programming landscape. First of all, is a language pure or impure? Meaning, is it actually based on pure mathematical functions, which gives some very nice properties, because some mathematicians in the 30s have devoted their whole life on computation. And we now have a device called a computer. Why do why don't we just take, all that pure mathematics and just apply it over there? It's like just a treasure there to be mined. So in the impure camp, we see a lot of languages. Now, the unfortunate thing for the programming, the fundamentalist functional programming community, is that those languages make a lot of money. Definitely, if you look at the amount of C code written and C# code and Java code and, all those imperative style languages, even though they're impure, they're immensely successful. Then at the bottom right corner, we have a fundamentalist pure functional language called Haskell. It doesn't make any, euro cent a day. It's, just there for academic stimulation purposes. But at the same time, it's very pure. It has some very nice properties. And if you actually look at Haskell, they've implemented things like software transactional memory, and it sort of works pretty nicely compared to the software transactional memory attempts that people have made in, in the imperative landscape, with imperative style runtimes. And they also have very lightweight parallelism. So maybe at some point when this multi-core thing becomes so omnipresent, the pure functional languages will actually make sense. So, of course, the question is there some nirvana where we have unicorns and rainbows and, sunshine and everyone's happy, makes lots of money and can still be pure? That seems to be the ideal world. The question, of course, is F# that particular language in that top right quadrant, or is Scala that next language, or is Clojure that next language? Like, there are lots of languages competing for being, a functional language that's mainstream. Well, I would say no. All those languages are still, in the camp that doesn't make that much money and isn't pure either. So it's, none of the two. However, they have some interesting properties like very concise code and those kind of things, and I would definitely encourage people to take a look at those because they sort of change your mind. The way you're thinking about writing your programs is still based on those little pieces of code, functions passed around as lambda expressions. And if you look at JavaScript, people are doing those kind of functional style things there quite often now as well. So far for fundamentalist functional stuff. Let's take a look at dynamic programming. So dynamic languages definitely have come along and become quite popular in the last couple of years again. If you look at the whole JavaScript community and Ruby and Python, it's definitely the case that those languages are gaining more attention again. Now the thing is that both dynamic and static languages have a lot of useful properties and nice properties about them, such as, for example, in dynamic languages, they are very simple and succinct. Now, if you actually looked at the F# code that I just wrote a minute ago, well, that code definitely is simple and succinct. Simple, well, if you know the paradigm, the functional programming or functional style programming paradigm quite well, but they're still completely statically typed. So what's really going on here is that there is some fertilization, cross-fertilization between the two domains going on. If you, for example, look at what static languages used to promise as heaven on earth, being very performant and having intelligent tooling, well, I would say that dynamic languages today have intelligent tooling as well. Like if I go to the website here, I do have 12 and script. Well, I basically have a debugger for script in a web browser, which is dynamically typed. So those things are not just fundamentally true about static languages alone anymore. So things are really getting mixed up quite a bit. So the thing that's going on here is this, sort of influence between both domains. Now, let's actually take a look at why we see that dynamic language trend coming back. So it's definitely the case that a lot of frameworks and a lot of platforms are going for, in the data space, for non-schematization. We used to have, things like XSD and WSDL and all of that stuff. Well, nowadays, people in the cloud, atmosphere, I would say, are much more tempted to just get rid of those things and say, let's do things untyped and dynamically typed, and it just works, In my opinion, it's more like duct tape, and that's actually a pun on duck typing, but, that's also about dynamic. But no, that seems to be the trend, that you have an increasing amount of services that, are based on that kind of loose typing, so we better can interoperate with those kind of things. Now, secondly, we have this next browser war, I would say, where people are really going for making things that run in the browser, like JavaScript, blazingly fast. And actually, they're succeeding quite well. If you look at engines like V8 and Chakra, you see that the performance of JavaScript in the browser is really taking scales that we've never seen before. So that sort of disproves that static languages are ideally suited or the only candidates to be very optimized. Still, there is a lot of art going on in making that happen. And then we also have this trend of metaprogramming, where basically programs manipulate programs as data. Things like Ruby on Rails have actually made this thing big. Now, we see getting those kind of code as data mechanisms become more available in much more places. Like if you look, for example, at the .NET framework, historically there has been a way to represent code as data. It just wasn't very meaningful to do real metaprogram using it. Like if you look, for example, at code DOM, well, you could generate code, but that was about it. Then later on, we started generating things like link expression trees in the dynamic language runtime, which is already a much more lightweight way of actually starting to generate pieces of code as data and then sort of compile them at runtime and have some thing going on there that basically is building code at runtime. And towards the future, we'll likely see things like compiler as a service, where you really have this metaprogramming capability as a first-class service right inside the framework. So things are evolving in that space as well, but all of those have to do with some kind of dynamism, whether it's dynamism at the type system level or dynamism by representing code as data. All those things really have to do with dynamic. So let's actually drill down a little bit in why it is that today the performance of those dynamic languages has really gotten to a point where they have become acceptable. So this piece of code is actually stunningly simple and polymorphic in some sense or polylinguistic, I would say. You can actually run the same code in C# and VB, not VB, C# and JavaScript, because the syntax is exactly the same. It just means two different things. If you write this code in C#, it's certainly statically typed because the var keyword does, implicit type inference. So in this case, because you assign 0 to A, the compiler knows that, the type of A needs to be int. And similarly for the I loop variable that exists in the for loop, we know that it's an int. Now, as an implication of that, if we have two int values, we also happen to know that there is an add instruction in the CPU. And actually, when we're talking about C#, it's one distance away because we know there's an add instruction in the IL instruction set that basically can just take two int32 values and add them together in a very fast fashion. So this is all the code that needs to be generated in statically typed languages, including languages like C and C++ would do exactly the same, but without the middleman of some IL code. However, if you start to change things a little bit, in terms of the runtime on which you run this piece of code, say you're running this thing in JavaScript, all of a sudden I and A in this piece of code do not have a static type. What's happening instead is that at runtime we have a little object that contains the value, in this case 0 and 0, but it also contains a type tag that's based on the assignment or the current value that's in that little box. So if I would assign, I some string later on, like, string Bart or something, the type tag would change and the box would contain, a reference to a piece of string that's sitting, in the heap of the process. Now, all of a sudden, in order to make this thing now work, dynamic languages need to insert a huge amount of plumbing. In this case, to look at the type tags and then see, well, I have two int32s here, and I happen to know there's an instruction to add those two things together. Well, let me actually fetch those values out of the box and cast them to the right, structure, and then give them to an add instruction. And ultimately, when things have been computed, I need to box that thing up again, because then I need to give it to the next operation. So there's a lot of stuff going on, machinery going on, to make a dynamic language really work on a platform. And now if you add to this thing interpretation, like an interpreted language, well, you have much more stuff to worry about again. You need to have something that fetches the next opcode and does that whole dynamic thing and sort of loops back and goes to the next operation, in this case, to execute the for loop. So compared to just a raw instruction to do an add, you really have several orders of magnitude here, 1, 2, maybe even more, in terms of cost that you need to have to do a simple addition of two integer values. Now, over time, languages, or actually runtimes, have been improved quite significantly to cut out those additional costs. So if we look at interpreters, interpreters have all of this. Ultimately, they need to execute some operation, which is the cheapest thing, but all the cost comes from interpreting the code that you've written, then doing some dynamic typing resolution, and ultimately call into the operation and then do some opposite things to sort of be friendly to the next guy in the pipeline again. JIT compilers have definitely taken away this interpretation part. If you look at things like the CLR, where you basically give this IL code and it gets JIT compiled into something that's very efficient, you're basically cutting out this interpretation part of the execution, and things get a lot faster. Now finally, with an adaptive JIT compiler, we can actually make things even faster. And the way that works is by just doing that type checking once and basically compiling some efficient piece of code that's dependent on the operation you're executing. Like if you have a dynamic call site where you have an addition between A and B, and you're doing that addition between A and B 1,000 times for 2 int32s, we do not need to basically start emitting that same addition code all the time. We can basically say, we have been here, we've seen 2 int32s before, hence we can do some very optimal piece of execution here that's based on caching instructions. And that's called inline caching, type specialization, those kind of things. So that's actually what we have in things like the dynamic language runtime. It's also some of the tricks that engines like JavaScript engines are playing nowadays. They basically do lots of analysis of your program to make sure, well, this thing can only operate on ints. Hence, they're sort of restoring some typing info at runtime to be more efficient. So dynamic languages are no longer, too expensive to be actually realistically useful. At the same time, I wouldn't say that now you should start throwing away all your types, because there are still a lot of advantages associated with having type information around and sort of validating the correctness of your program and your assumptions early on. And that's what I like a lot about type systems. So what do we have in the package for the DLR, the dynamic language runtime in .NET 4, is all the facilities at the runtime level, and again it's painted in red, which means it's close to the metal. It's something that realistically you don't have to care about that much. Contains expression trees, dynamic dispatch, and call site caching, which is a way to optimize those instructions. On top of that, we have a lot of languages, including C# and VB, but also the prominent dynamically typed ones, including Python and Ruby, for example. And then we can bind to a lot of things. We can, for example, bind to JavaScript, which is running in the browser. So we can basically just dot into the HTML DOM from a dynamic object that lives in, for example, Silverlight, the script object APIs. So let's actually have a little look at the dynamic stuff we actually have available in .NET 4. So I do have dynamic stuff sitting here. So I do two things here. I want to look at dynamic from a data angle and from a code angle, because those two things really are complementary. Well, that's actually where all the modern machine architectures are based on, the fact that you have code and data. The first thing I want to do here is interoperate with Python. So the thing I'm doing here is I'm getting a calculator object. And this calculator object really comes from IronPython. So I've defined a calculator object that actually sits in a file called calc.py. In fact, I've installed the IronPython SDK, which is available on Codeplex. And so you see some syntax highlighting here because I'm in a .py file. So you see that parentheses are colored in some green color. And I have some syntax highlighting, so it's not just a notepad file anymore. And so I'm just defining a couple of things here just for fun and giggles. I'm defining an instance method on a calculator type. Of course, it could be a static method as well. The way you declare an instance method in Python is by actually passing in this thing called self, which is the same as this. And so this is just a very simple way of just adding two things together. However, I haven't said here that A and B need to be ints. Because IronPython is built on top of .NET Runtime, if I would have a vector class and another vector class, and those define an addition operator between the two, this code would perfectly work. You could call calc.add of two vector objects and it would work. Or you could call it with two string objects and it would work because it's dynamically typed. at runtime it will look for some operation that can add the two things together based on the type. Now the thing that's going on behind the scenes in the dynamic language runtime is that it basically builds for this particular dynamic call site where we add two things together. It's building a cache of optimized instructions for every pair of those two inputs. So if I call this call site 1,000 times with two int32s, it will go almost as fast, as a statically typed language that adds two int32s together, because it has been there, it has done all the resolution rules, and once it knows the operation, it can emit some very efficient IL code that just adds those two things together. So we don't always have to go through the slow path of all the resolution of an operation that can add two ints together. So the way to interoperate with that is just, you can import some hosting APIs. And you just find, when Python is installed, you actually find things like Microsoft.scripting, which is an Uber API to expose scripting objects. You have IronPython here, and there is some namespace in there that's called ironpython.hosting, and there we can actually get some engine. And so once we have a Python engine, we can say, please create some script file from, some file on disk. We just load that whole thing, we execute it, so it basically has loaded all the types. And then we expose, from the scope we actually call getCalc. And getCalc is just, a top-level global function, a function not in the pure sense again, that's defined here by Python to basically return a new object of type calc. So now I have my calculator, and the way I leak it out to C# code is by basically returning a dynamic. This is, the thing that we had most fun about when dynamic came online, that you now can write something like static dynamic. But, it just is another type. And this means that whenever we encounter a dynamic object in a call site, like over here, I have the calc object being dynamically typed, I do not get any IntelliSense. And I can just write whatever I want to do here. And I'm basically calling the add method dynamically. So that means if you now have one of those APIs that looks very promising in Python or Ruby or any dynamic language on the DLR, you can just interoperate with that from regular C#, Visual Basic, any language that you see fit. And those things can truly, call each other. You could even pass in, a little delegate to a little piece of C# code that then needs to be called back by the Python code. Like you truly have interop between the two places here. Now, here I'm just adding 1 and 2 together. I can also call this calculator thing that does a plus operation, given a datetime.now and a time span. And for that, there is an addition operation available. If you actually look in, the IL or, any way to visualize the datetime type, you will actually find a static method called up_addition that basically implements an addition between a datetime and a time span. And so Python can resolve that and actually be very efficient subsequently about executing any computation on datetime and time span in this particular dynamic call site. So in here, we'll really get some code that looks like if A is an int and if B is an int, then I will do this very efficient thing. If A is a datetime and B is a time span, I will do this efficient thing. And that's all based on generated IL code at runtime. Now, that's only the code axis, and of course, I should prove that this actually works. If I press Ctrl F5, you basically see 3, which is 1 and 2 added together. And then we see, tomorrow will be the 27th of April at 2:42 a.m. I'm still on a different time zone. So that's actually executing code. We can also dot into dynamic pieces of data. And that's something that's very interesting if, for example, you have a JSON API, and, well, JSON objects that come from JavaScript are dynamically typed. So how do you actually interoperate with those? Do you want to do something like JSON.getMember and then pass in the value as a string and all of that stuff? The answer is no. You can actually create a dynamic object that wraps around that particular piece of data. In this case, I'm dotting into an XML API, which is a little tricky because XML is, in my opinion, fundamentally broken with regards to the axes that exist. You have XML elements can have attributes, and they can also have, child elements. And because you have those two things sitting there, you can't just say what the dot operator needs to do. Does the dot operator need to search for attributes, or does it need to search for child elements? That's something that's not at all clear. So in this case, I'm just overloading the dot operator as you can see over here, to dot into attributes. If I would have child elements here, I would have to make a choice. But so I'm just getting out of that. And what I'm doing is I'm creating an XML dynamic object that passes in the X element that I've declared over here. And this XML dynamic object actually derives from dynamic object, which lives in system.dynamic. And this is basically your way for your code to communicate with the dynamic language runtime back and forth. So now you get basically interceptions for things like try get member. So if I set a breakpoint over here, what will happen is that the compiler has seen that this thing is assigned to a dynamic variable. So it basically generates a dynamic call site to get the member called name, and it passes that in some little piece of information that contains the string name. And ultimately, that thing, through the magic of the dynamic language runtime, will end up calling try get member, where you get a chance to basically say what it means to dot into the name property on that particular object. So let's press F5. And as you can see, I have a binder object being passed in that, have a binder object being passed in that actually says, well, I'm looking here for something called name, and ignore case is set to false, which means I'm coming from C#, and the user actually prefers to have case-sensitive lookup because that's what the language is doing. Now, if you would come from Visual Basic, ignore case would be set to true. So now that I have, the thing that the user tries to do, and actually if I go up here, you will see that I have a gray line, so I'm really executing d.name is d.h. You see that there is some external code going on here. And this external code in the call stack, I will actually read it out loud. First of all, calls into some system dynamic stuff, which is like the entry point of some DLR. And then you see some lightweight function. That's basically that efficient call site being generated at runtime. So that's the way that a dynamic language runtime can actually optimize things, because it always updates that call site by adding new instructions to it for the particular things it sees. So in this particular case, it will be able to remember things like, you're doing a name resolution on that particular object. Well, I've seen that before. I can go quicker into a particular piece of code that's very efficient about that. So ultimately here what I'm saying is just, given that name, which is also called name in this case, I will just look up that attribute, and I found the attribute. It has a value of Bart. I will just assign that to the output parameter that's sitting over here. And then ultimately, if I step out of this code, you see that if I step in again, now we are in a piece of code that executes the resolution for the age property. So we've already gotten to the name. Now we're actually asking to get access to the age property. That's part of this expression. And again, we go through the same motions. We dot into the XML APIs, which is the thing we want to shield the user away from. Like, the user doesn't have to know he has to go into dot attribute and pass in a string and then do dot value on that thing. We can do all of that stuff for the user, so that's the thing we're doing here. And the result actually comes out as 28. And so ultimately, this thing prints on the screen Bart is 28, which actually happens to dynamic calls to my dynamic object. So it's very easy to wrap some existing API that's intrinsically dynamically typed and sort of get rid of all that plumbing that you have to do manually. Think about the data set with data tables where you have to do square bracket lookups to get into the table and square bracket lookups to get into columns. Well, you could basically wrap your data set using a dynamic object and then just dot into that. The thing you're losing is static typing, but in the first place, you didn't have types to begin with, because if you dot into a data set, ultimately at the bottom of the API, what you're going to get back out of a row with certain columns will be system.object objects, where you don't have any type information to start with. The only thing you sort of had to do is put all of your code in square brackets and strings and call magic APIs and do a little bit of snake oil over there, and the thing works. Well, with dynamic, you can actually get rid of all of that ugly code without really losing any typing, because you didn't have typing to begin with in those particular APIs. Now, that said, if you do have typing, that's meaningful. I wouldn't start doing everything using dynamic, because it's still more expensive, and it will always be more expensive, I would say. And at the same time, you're just tossing away the baby with the bathwater, I would say. So far for dynamic. which I think will become increasingly interesting if you see all those APIs exposing JSON. Like a couple of weeks ago, I was basically doing the exercise of building some link providers. That's what I now start to do for a living, actually, on my team, which is great. And so I was writing a lot of link providers to cloud assets, like lots of things that live in the cloud. And the way those things expose APIs is by means of JSON objects, or they have some magic API that takes in, that's based on REST. And really, what you want to do is not have to basically push yourself through some URL strings and push yourself through some ugly JSON API. You just want to be able to dot into those objects. And so the blend of, using dynamic together with those things that acquire data from the web is actually pretty interesting, in my opinion. So as an extension to that, and I'm pretty sure you've seen this slide before, we're also working in the language teams, the C# and Visual Basic language teams, on opening up the compiler. Historically, it's been that the compilers for .NET languages have been pretty closed, meaning that you pass in some source files, then out come some assemblies, but in the middle you don't have any control over what's happening. And so what you see is that a lot of people have written little parsers, most of them incorrect for languages like C# and Visual Basic, just to do some analyses on some piece of code or to write some refactoring engines. So the thing that's going on, and that's an ongoing development effort in the developer division, is to actually rewrite the compilers using C# itself, C# and VB itself. And those compilers will actually have some big API on top of them, big in terms of spanning the entire language surface, so that you basically get access to what the user has written in code. So you will actually be able to see like declaration units and the definitions of methods, so that you can start writing things like method programming engines on top of that. You can write read evaluation print loops. You can do things like embedding a language into another language, because you can sort of access those trees. It becomes possible to do embedding of languages. And because you have an object model, well, because you have that, you can start writing refactoring mechanisms and those kind of things pretty easily. In fact, one of the demos that we've given recently is taking the language object model for C#, just translating into VB and doing a toString on it. And you can basically just toss your code from C# into VB and vice versa, because those language models are sharing the same underlying APIs. It becomes possible to have that interoperability at that level as well. So now, moving on, and the reason I actually put this compiler as a service in the dynamic camp is because of the meta programming facilities. Another trend that we've looked at in the introduction, and that's the last one I actually want to talk about, is concurrent programming. We all know what the problem is, I guess. Windows can run on 256 cores, and actually this thing is pretty busy because it's running SQL Server, which parallelizes pretty nicely, as you can see. But in general, your console app or your WinForms app or your web service app doesn't quite scale to this level. So what's the problem? How can we keep those, all those cores that we have in the machine busy? And actually, this machine has 8 cores, and likely, when I come here next year, I will have 16 cores with me, and most of them are actually idle. In fact, let's just take a look at what's going on. In the resource monitor, I will see the embarrassing fact, I guess, that if I go to CPU, you see that Windows 7 has sparked core 0, it has sparked core 3, it has sparked core 5, and it has sparked core 7. It basically has decided there's no work to do. Just 4 of your cores are not doing anything because they're powered off by the operating system, which is happening in Windows 7 and Windows Server 2008 R2. So really, my investment of 8 cores isn't paying off here, definitely not during my presentation. So how do we keep those things busy? Well, the thing is that shared state is just a beast, right? I'm currently working on things like RX, the reactive extensions, which is about event processing systems. And events can come in on different threads. And then we have to sit there and stare at the screen like, how are we going to do logs that are short-lived here and work with this shared state because we need to talk to the same observer object and all of that stuff? And if you're not careful, you're basically just deadlocking the whole crossing. So that's not a good thing to actually use as a sledgehammer approach to doing parallel programming. Like logs are not very compositional. They don't quite scale to the level that you want them to be, because fundamentally they're about reducing, parallelism in the system. You just want to wait for some other thing to be complete. So maybe locking is not the answer, but then what's the answer? And actually this slide is not, to be the answer to my question, what's the answer? It's basically, some way along the line of trying to solve the problem, but it's still a long way off. But what we can do for sure is give you better primitives and better mechanisms to do those, parallel programming things in your APIs and your applications. So in .NET 4, we introduced the whole parallel extensions, including the TPL, which gives you a lightweight form of, execution called task of T. And in fact, in the next versions of the framework where we're doing async and await stuff, task of T will get much more lightweight than it already is. So the idea is really to make something that's much lighter weight than operating system threads, because operating system threads actually take some memory, like they have some stack space. They are quite expensive to actually allocate. We also have things like the coordination data structures, which give you lightweight synchronization primitives. For example, if you really use a manual reset event today in your code somewhere, you should consider looking at the .NET 4 manual reset event Slim, which is basically a more lightweight mechanism to do the same thing, but it avoids going into kernel mode that quickly, which means it's more cheap than other more fundamental mechanisms that are built into the operating system. So you can make your programs already faster if they're using those synchronization primitives, but you're not really addressing the problem of the multi-core from the bottom up, I would say. So let's take a look at TPL a little closer. There are really 4 things to it, I would say. The things that you will see most of the time are the ones on the top, task-oriented programming and data-oriented programming using task of T and P-link. You will also want to look at composition. So basically, if you have a task, you can do things like continuations, which means you have a task and then you say, when the task is complete, please execute this piece of code, so you can build those pipelines of operations. And then the whole coordination and scheduling thing, well, the scheduling thing is a very low-level mechanism, really. The coordination data structures are still, specialized, specialist use, I would say, but are very useful to take a look at as well. So using this from a language angle, we can actually say that we're pretty happy with the result, because if you look at the differences between some non-parallel code and the parallel code using the parallel.4 static method, you see that the two really look pretty much the same. And that's thanks to the language really being to a level where we have, expressiveness with lambda expressions, extension methods, those kind of things, that you can build those fluent APIs. In this case, I can just do parallel 4, and I can pass in a lambda expression. Now, one of the things that this thing doesn't solve is, well, if you have a lambda expression, what does it mean to break from the loop? Can you break from the loop using this particular piece of language syntax? And the answer is no, because, well, a break keyword inside a lambda expression doesn't really mean jump out of the outer loop, because you're sitting inside a lambda expression. So it's limited, but it already gives you the ability to write those rich APIs that look exactly the same as the original ones, or actually mostly the same. But they have some caveats associated to them. And actually, the task parallel library gives you a way to break out of a parallel loop. You basically pass in a parallel loop state as well, and then you have to call a break method on it, which looks pretty similar to a break keyword as well. Now, the truth is that this little sample I've given here is what we call embarrassingly parallel. This is parallelizing a little loop, and the way it does so is by just spawning a different task for every row in the matrix, the result matrix of which I'm doing a multiplication. And that's something that really lends itself very nicely to do parallel programming. In fact, this is even more of data parallelism than task parallelism, I would say. Here we have another example that's called plink, the parallel link APIs, which basically says, well, in order to parallelize your code, the only thing you need to do in your link query is call sParallel. And again, that's an embarrassingly parallel problem. However, there are some little things sort of staring at you in the code that you have to be very careful about. Say that your where method here, or your where filter, calls into an F function that does something with shared state, well, task parallel library is not going to prevent you from mutating state, which is now being mutated in parallel, because there will be multiple where clauses running simultaneously on different cores. So while we can have the expressiveness in APIs, it's clear that at the lower level, we need to have more constructs in the languages to allow you to basically be safer. In this case, if f of x would really be a pure function, we would know this is dang safe. And in fact, that's what certain database engines actually use as a property to make sure that, that your code basically cannot blow up the database engine. Well, you better have two parallel things that do not conflict with each other. But the thing here is that we have natural data parallelism. In this case, we just have a piece of data. Well, we can partition that quite nicely to do parallel wheres and parallel selects and all of that stuff, and then aggregate the results together at the end. So it definitely works to have those things available, and they're very valuable. They're easy to try out. You don't have to overturn your entire code in order to parallelize it or try to parallelize it. But it's really, to be honest, it's at the low end of the spectrum. There's much more work to be done in the concurrency space, and that's something a lot of languages are looking at. For example, if you look at Erlang and some of the functional language community, they're looking at more isolation and state-free programming, which is stuff we're also interested in looking at ourselves. Now, one of the low-hanging fruits, I would say, of the concurrency space is something we're doing for the next version of C# and VB, which is making this thing called asynchronous programming easier. The fact is that your applications are really interacting with a lot of APIs and a lot of systems that are intrinsically asking for asynchronous communication. For example, in JavaScript Silverlight Windows Phone, the only way you can talk to a web service is asynchronously. So can we make code actually better in that world, where, for example, you do asynchronous I/O, you're doing event-based programming and those kind of things? Well, the answer is yes. We actually have something called the async CTP that allows you to do that. So over here I have a little piece of code that does download data. You could actually say web client.download string. That would be a pretty good sample of that. I've just chosen a more generic name. In this case, it's a blocking call, which means that my thread is just frozen. It can't do anything really until download data comes back, and then I will process the data. So this is clearly not a good thing for responsive UIs and those kind of things. So in order to make this thing async, historically you've been asked to actually do those unnatural acts like this, where you say, instead of calling download data, I now need to call download data async or begin download data. And I need to pass in some callback function. In this case, I'm passing in a lambda expression that will process the data once it's available. You also have event-based APIs, like the asynchronous .NET asynchronous pattern based on events would actually have a completed event. Now, the thing is that your code starts looking inside out. You don't have sequential flow anymore. You don't have code that looks as nice as the one on the left. In order to go asynchronous, you basically need to restructure your code using all those ugly callbacks. And it gets pretty ugly pretty quickly. So in the async CTP, what you can do now is you can actually call APIs like download data async, and you can put a little keyword in front of that called await. And what happens there is that the thing is still executed asynchronously. If you do that on the UI thread, your UI thread is free. As soon as it has started the await operation, it can do other things. And what happens is that the compiler basically turns that code into the code that you see on the line above that. It basically takes everything beyond the await into a callback and basically rewrites the code for you. And so your code now looks sequential. You can put this in while loops and for loops and everything. You can do try-catch around it. And you will really catch exceptions that come out upon completion or upon beginning. Like all the control flow just works. So that's actually something coming up, and you can actually download the async CTP today. So very quickly, let me give you a little example of contrasting two pieces of code here. This is the Netflix example. So first of all, I have Netflix synchronous. The synchronous Netflix sample, where is it? Is that the synchronous one? No, that's the today one. That's the synchronous one. The synchronous one essentially does things like client.download string, which is a blocking operation during query movies. So if we're querying movies from the Netflix service, we're basically blocking. Now, if I want to restructure that code, the query movies code, to basically be async, I need to do a lot of grueling tasks, as you can see. I need to create a cancellation token, I need to download string completed, have a lambda expression that contains all the logic when the thing returns. My code doesn't look sequential anymore. So to solve that, the async CTP allows you to basically write things using the await keyword. Now you can do things like await client.download string task async, and the task part in here is just a temporary placeholder. But what you're seeing is that the code looks exactly the same as it used to look in the synchronous case. And this code completely gets lifted into this, asynchronous callback-based mechanism. Just to prove to you that it actually works, I can do 2010 here. And basically, while the search is going, you see the results are coming in one by one asynchronously, and my UI is still snappy and responsive. I can basically move things and start, scrolling in here while the thing is actually going. If I would do that with the synchronous one, my UI would be stuck, just tremendously while it's actually doing that. So the synchronous API, 2010 search, well, I'm already stuck. The thing is now downloading all the movies, and things are going terribly wrong. The only thing I had to do to make this thing async is just put some await keywords in to make those operations basically schedule away their continuation. Which is a pretty nifty feature, and it's still going and it's still being blocked. So might return, in the next couple of minutes. So for concurrency, there's still a lot of work to be done. You've seen some investments in async, you've seen some investments in the TPL and things around that to make it easier to express things like parallel loops. But definitely there's more stuff to look at, like for example, if we make things immutable, they will be easier to basically be parallelized. What about purity? That's the whole functional programming debate. If you have pure functions, well, because they don't have side effects, those pure functions, you can run them in parallel. So there are a lot of open questions in that space, and you will definitely see more coming around that in the near future, and also the long-term future. So I would say it are exciting times. If you take a look at all those trends that you're seeing, a lot of them are already readily usable. Like the whole dynamic space, I think, is pretty promising. If you look at engines like the JavaScript engines, they're darn fast today. So the dynamic question sort of has been solved. There are lots of outstanding questions with regards to concurrency, with regards to where functional programming would fit in. And so I would definitely encourage you to learn some other languages, just for fun in your free time. Take a look at something totally crazy that you're not comfortable with, like Haskell is a very good choice to just get your brains blown apart. But you will start thinking about things in a different way. You will structure your code in a way that might be more natural fit for certain problems. Like certain things lend themselves much better to doing things functionally than doing them, for example, in an imperative style. And you've seen the conciseness of languages like C# in that space, F#, I mean. So with that, I would like to conclude. I will be around for questions. So if you have any, please come to me. And I would like to thank you for your attention. Thanks.